Welcome back to this course on polymer chemistry. Till now what we have been learning for last several lectures is how to synthesize different polymers, how to make different polymers. We have learned different types of polymerization by which we can make polymers, and we now theoretically know that once we do a polymer synthesis, what are the different types of molecular weight and what are the different types of molecular weight distribution we can get from our previous learning from last few lectures. Now, what we are going to learn in next few lectures is that how to characterize. Once we made these polymers, of course, we want to know that what we have made, both in chemical term, that means what is the constitution, what is the chemical constitution, what is the structure, microstructure of the polymer, and also most important is what is the molecular weight of the polymers which we made, and what are the, as you know that polymers seldom have unique same, all the polymer chains have same molecular weight. So, there will be always a molecular weight distribution associated with when we make a polymer. So, what the polymers which we already synthesized, what is the molecular weight distribution. Now, for that what we will begin today is to know what is to understand polymers in solution, and in today's lecture we are going to learn lattice theory of solutions for small molecules, and then learn about ideal solutions, thermodynamic probability and distribution, Boltzmann equation, and then learn about polymer Huggins theory of polymer solutions. These are the subtopics which we will learn during this lecture. Now, as I said that we are going to learn polymers in solution or polymer solutions. Now, why do we need to study polymers in solution? As I was just mentioning that once we made these polymers, we must characterize both chemically and physically, and one of the most important parameter is the molecular weight. Now, as you will see in after few lectures that most of these polymer characterization techniques, for example, molecular measurements, chemical characterization, etc., are done in solution. So, unless we do not know how polymers behave in solution, we will not be able to understand how polymer characterization is done. Also, many of the applications in the beginning, if you recall, I mentioned that there are few applications or some applications where, though in not majority, a minor application of polymers where polymers are used in solution. For example, eye drop, where the water soluble surface active polymers are used, detergents, and there are several applications where you will find that polymers are added in solution. So, polymers are used in the applications where the final form of the product is in solution form. So, we must know the behavior of the polymers in solutions to understand how we can utilize these synthesized polymers in those applications. Also, biomacromolecules, for example, proteins, nucleic acids, though these are not these polymers are not part of this course, but as a comparison, biomacromolecules they function mainly in aqueous environment, and to understand the behavior of these biomacromolecules, one must understand the solution behavior of these molecules, and the solution behavior or thermodynamics of polymer solutions is for the synthetic polymers are very similar to the treatment you will see for biomacromolecules. So, if you understand the thermodynamics of polymer solution for the synthetic polymers, you will also able to easily understand the behavior of macromolecules in solution, biomacromolecules in solution. So, let us start with thermodynamics of polymer solution. And what is solution? We know, as we know, that a solution can be defined as a homogeneous mixture of two or more substances. Homogeneous means that the mixture is at molecular level, and of course, we know that from our basic understanding of thermodynamics that usual thermodynamic condition of constant temperature and pressure for two component system, spontaneous formation of solution requires that the Gibbs free energy of the solution is lower than the sum of the Gibbs free energy of the solvent and the solute G1 and G2. And in other words, you can write that Gibbs free energy mixing, Gibbs free energy which is given by the difference in the Gibbs free energy of the solution or the mixture and the sum of the individual Gibbs free energies of the solvent and solute should be negative 2, so that the solution can form spontaneously. And we also know that this Gibbs free energy of mixing can be expressed in terms of enthalpy of mixing and entropy of mixing. So, this should be lower than 0. Now, let us start with ideal solutions of small molecules. Now, ideal solution is a mixture of molecules having identical size. We call a solution as an ideal solution when the ingredients, all the components, solute and the solvents are having same size, the individual sizes, molecular sizes are same, and once the molecular size is same, molar volumes are same, then mole fraction would be equals to the volume fraction, and the change in or volume of mixing would be 0. So, there will be no change in volume after mixing of the components. And of course, there is another condition that force acting between the like and unlike molecules, similar and dissimilar molecules are equal, or in other words, if you have say 1 is your solvent and 2 is your solute, then interaction between 1 solute solvent and 2 solute is same as the interaction between a solute and solvent molecules, which is 1-2 interaction. So, if you replace one of the molecules, say solid molecules or solvent molecules, with another one, there should not be any change in the energy of the system. So, energy of mixing should be 0, and as we have seen that volume of mixing is also 0. So, enthalpy of mixing should be 0. So, ideal solution formation leads to a thermal mixing, okay, with no change in enthalpy of the system. Now, if there is no change in enthalpy of the system on mixing or when the solute and solvent mix and form a solution, the entropy of mixing delta S m would depend only on the combinatorial entropy. The other entropies like translational, vibrational and rotational entropies associated with the molecules, they will not change at all, because there is no change in thermal energy in the system, delta H m is 0. So, those entropies will not change. So, on mixing the only change in the entropy would be the combinatorial entropy. And what is the combinatorial entropy or configurational entropy? Is the number of ways you can arrange different molecules, number of distinguishable ways you can arrange different molecules. So, the more number of such numbers, then the entropy of mixing is higher. So, mixing becomes easier. Let us discuss little more in next page. Combinatorial entropy of the system is given by the number of possible distinguishable spatial arrangement. So, for a given state, we know from our statistical thermodynamics or statistical mechanics that Boltzmann equation gives the relation between the combinatorial entropy and W, which is the number of possible distinguishable degenerate arrangement. W is the possible distinguish, all the arrangement you are doing by changing the position of the molecules has to be distinguished and they has to be of same energy, because in this case of ideal solution, because their interaction energies are same between like and unlike molecules. So, once if you do interchange between solute and solvent molecules, they will produce degenerate arrangements. Now, let us talk about how to calculate this combinatorial or configurational entropy, and we are continuing our discussion with the most simple system of ideal solution. And let us have you have N1 is the number of solvent molecule and N2 is the number of solute molecules. And N0 is N1 plus N2, which is the total number of molecules. Now, we have said or we have seen earlier that in case of ideal solution, the sizes of the solvent and the solute molecules are similar. So, we can have a one 3D cell, 3D lattice, which have N0 a number of cells, and the size of the cell of each cell is same as the size of the one molecule. Now, in this slide it is shown as a 2D one of the 2D version of the 3D. You can imagine that it is a 3D lattice. So, now we have N0 number of cells and N0 number of molecules, and each size of each cell is equal to the size of one molecule. Now, let us we put or place the solute and solvent molecules. Solute are and will be shown as number 2 in this course, and it is typically shown as 2, and solvent will be represented as 1. So, N2 number of solute molecules and N1 number of solvent molecules, which are shown in these colors, and total N1 and N2 is the total number of molecules, and they are placed randomly in this cell. So, now you have to calculate how many different ways you can arrange these molecules. Now, total number of molecules is N0 is N1 plus N2. So, total number of ways you can arrange these total molecules is factorial of N0. This is the number of ways you can arrange all these molecules. Now, if you replace one solvent molecule with another, or you can change the position of the solvent molecules with another solvent molecule, you can imagine that you are not creating another distinguishable arrangement. If you replace this one with, if you interchange this molecule with this molecule, you are getting the same arrangement. Basically, there these two arrangement of replacing one solvent molecule or interchanging one solvent molecules with another, or one solute molecules with another solute molecules will not give you any indistinguishable arrangement. So, these arrangements are overestimated. So, actual number of distinguishable arrangements would be, you divide by the N1 factorial and N2 factorial. So, quickly. The combinatorial entropy will be given by Boltzmann equation. I will just do quickly, plus n2 factorial divided by n1 factorial and n2 factorial, and for large n, large value of n, Ni, Stirling approximation gives you ln n factorial is, this is from your previous mathematical knowledge. So, you can apply this and you can write S is equal to K n0 ln n0 minus n0 okay. This is just, this is n0 factorial. So, you can just use this Stirling approximation and you get this expression. Now, I continue further simplification, you will get this K is Boltzmann constant, as you know previously. Now, mole fraction represented by xi, or I can write capital Xi. Mole fraction is Ni by N0. So, S would be given by K N1 ln x1 plus N2 ln x2. This is the S for the mixture. So, I can write this is for the mixture Sm. Now, for pure solvent and solute, what will be the W? Number of ways you can arrange is 1, because no matter how many times you interchange the molecules, you will always end up in same arrangement. So, there is only one distinguishable way you can arrange a pure solvent or a pure solute. So, W1 is 1 and W2 for the solute is also 1. So, S1 is 0 and S2 is also K ln W2 is 0. So, this is the entropy, combinatorial entropy for the mixture, and this is the entropy for the solvent, and this is for the solute before mixture. So, what is the entropy of mixture mixing in this case is Sm, entropy of the mixture S2 is given by Sm, and it is the same what we have seen earlier. You can multiply it both sides by convert it to N1 is the number of molecules, solvent molecules, and small m N1 upper lowercase n is your number of moles. solvent, number of moles of solvent. So, N2 is the number of moles of the solute. Now, what is del Hm for the ideal solution is 0. So, del Gm, which is gives free energy for mixture, would be del Hm minus T del Sm Vkt N1 ln x1 plus N2 ln x2 or RT N1 x1 plus N2 x2. Okay. So, this is your expression for Gibbs free energy of mixing Gibbs free energy. This is the mole fraction for solvent, this is for solute, this is number of moles for solvent, and this is number of moles for the solute. So, we can write for this ideal solution, entropy of mixing is given by this expression, and remember this is the same as we have seen from Raoult's law, which gives the expression of entropy of mixing for gives free energy for the ideal solution. Now, what about non-ideal solution? Now, there could be three types of non-ideal solution. One is athermal, where del Hm is 0, but del Sm is not same as in case of what we just seen for ideal solution. Second is a regular solution, entropy of mixing is same as ideal solution, but entropy of enthalpy of mixing is not 0. And third is irregular, where enthalpy of mixing is not 0 and entropy of mixing also not same as the ideal solution. Now, non-ideal solution of small molecules is invariably due to a non-athermal mixing. Okay. Any, as you know from your physical chemistry knowledge, that any non-ideality introduced by any non-ideality which happens in case of solutions for small molecules are due to non-athermal mixing, or delta H mixing is not equal to 0. For polymer molecules, for polymer solutions, this non-ideality is generally due to both. It is both for non-athermal mixing, del H mixing is not equals to 0, and also contribution from other than combinatorial entropy. So, in case of polymer solution, the non-ideal behavior of polymer solution, or a polymer solution behave unlike a ideal solution of small molecule we just discussed. Because of both the reasons, it is in most cases the enthalpy of mixing or enthalpy of solution for a polymer in a solvent is not equal to 0, delta H mixing is not equal to 0, and also for ideal solution it is only the combinatorial entropy which contributes to the Gibbs free energy change for the mixing. In case of polymer solution, as we will see in a moment, that it is not only the combinatorial entropy, it is also the entropy change induced by the athermal process also contributes in the Gibbs free energy of mixing. And in most cases, vapor pressure of a polymer solutions are invariably much lower than what has been predicted from the Raoult's law, which is the law describing the ideal solution. So, how to get this combinatorial entropy or Gibbs free energy of mixing for the polymer solution? We have till now we have done the Gibbs free energy of mixing for solution, ideal solutions for small molecules. Now, we will try to apply the same lattice theory to find out the Gibbs-Phenom mixing for the polymer solvent mixture or a solution of polymer in a solvent. Recall that in case of ideal solution of the molecules are having same size, okay. But in polymer, obviously when you are dissolving a large polymer molecule in a solvent molecules, the size of polymer molecules are much higher than solvent molecules. So, this assumption which we made for ideal solution is not valid here. The sizes are solvent molecules and solute molecules, in this case polymer molecules is much higher, is very different. And in case in ideal solution, we had seen that del H mixing is 0 because of the force of like and unlike molecules are 1 1 2 2 is equals to 1 2, and in most often interaction between polymer and solvent molecules is not thermal. There are in most cases there are specific interaction between polymer and solvent molecule is different than the interaction between a solvent molecule or a polymer molecules. So, these are the two main difference of a polymer solution than a ideal solution of the small molecules. Now, the two scientists Paul Flory and Maurice Huggins, they proposed a theory which we will know in a minute, which took consideration of the large difference in the size for the solute, in this case polymer and the solvent, and existence of the intermolecular interactions. So, now what we will do, we will explain or we will try to learn how the Flory Huggins theory was established using that same lattice theory which we just learned for small molecules. Again, we will have the same 3D lattice in this case as well, but here the difference is that N1 is again the number of solvent molecules and N2 is number of polymer molecules. Obviously, the sizes of the polymer molecules and solvent molecules are different. So, what we are doing, we are breaking or dividing the polymer molecule into X segments, dividing a single polymer molecule into X segments, where the size of each segment is same as the size of a solvent molecule. So, X is V1, V2 by V1, where V2 is the molar volume of polymer and V1 is the molar volume of solvent. So, what we are doing, we are breaking polymer or dividing a single polymer chain into X segments, where the size of each segment is same as the solvent molecules. So, each polymer molecule has X segments. So, N2 number of polymer molecules has N2 into X segments. So, these are the total number of polymer segments in the solution or in the mixture. So, we require N1 plus N2x, which is N0, this is the number of lattice we require, where each size of each lattice is either same as the size of the solvent molecules or same as the size for a segment of a polymer. Okay. So, N0, we have N0 number of cells, where N1 is the number of solvent molecules. So, each size of each cell is same as the size of the solvent molecules, and X is the number of segment of a single polymer chain, and size of the segment is same as the size of the cell. Okay. So, we have n 0 number of cells. So, n 0 is given by n 1 plus x n 2. What I am going to do is find out first how many different ways we can arrange the polymer segments. We are going to add the polymers in those in this 3D lattice one after one. We are going to add the polymer chains in this lattice one after one segment after one segment, and once we added all the polymer chains, then we will add the solvent molecules. This is the approach what we are taking. We will add the polymers one by one, and for single polymers we will add each segment one after one. Now, how do we going to add these polymer segments? See, if we have already I is the number of polymers already added. So, we have already added in this 3 lattice, which we are not showing those I number of polymer molecules are not shown here to make this picture clear. Okay. So, you have to understand that there are already I number of polymers present, which means I into x number of cells are already occupied. Okay. Each polymer has x number of segment. If we had I number of polymers which is already added, so I minus x cells are already occupied. So, how many number of this is number of cells already occupied by the polymer segments. So, n 0 minus I x is the number of vacant cell, okay, where the next one the I plus 1 polymer chain we can place. Okay. This is the number of cells which are vacant, because n 0 was total number of cell and I x is the number of cells already occupied. So, n 0 minus I x is the number of vacant cells. So, this is the number of cells where we can place the next molecule, next polymer molecule, which is I plus month, I plus first. Okay. Now, I plus this polymer chain has how many segments? Again x segments. This I plus 1 or I plus first chain has x segments. So, the first segment of these polymers, let me write this is the number of vacant cells available for this I plus first polymer chains to get in. Now, the first segment, this first segment, now as I said earlier that I am showing these all are vacant, but these are not vacant. I x number of cells are already blocked, already occupied. So, n 0 minus x I is the number of cells which are available. So, how many ways, different ways you can place the first segment of the polymer? There are n 0 minus x I number of vacant cell. So, the first segment of the I plus first of the I plus first polymer can be added how many different ways? Of course, it can be added any of these vacant cells. Okay. So, it can be added in this many ways. Okay. Fine, clear? So, this is the number of vacant cells available for the segments to go in. So, you can arrange, you can place or you can locate the first segment in any of these vacant cells. So, this is the number of ways you can add the first segment. What about the second segment? If I want to add another molecule, another segment, not molecule, if I want to add another segment where it has to stay, of course, unlike the small molecules where the molecules are apart from each other, for polymers the segment has to be tied up because the segments are joined to each other. So, they can be placed in any of these first neighbor. Okay. So, if Z is the coordination number, Z is the coordination number, okay, which is the number of cells present in the first number. So, you can add in any of these cells. Okay. So, I can add, say I can add here. So, second segment can be placed in any of these Z cells. Now, what is the chance that all the Z cells are vacant? Remember, the lattice already has x I number of blocked cell. So, it is not that all these Z number of cells will be free for the second segment to go in. There is a probability. So, if I write the probability as P I, then the number of ways the second segment can be placed is Z P. Okay. P is the probability that the cell is vacant. Now, what is that probability? Total number of empty cells are n 0 minus x I divided by total number of cells. Okay. So, this is the probability, chances of that one of the cell, any, if you choose and pick any of the cell from this lattice, this is the probability that it will be vacant. Okay, because this is the number of cells which are vacant and this is the total number of cells present in the lattice. So, this is the probability. Okay. And this is the second segment, number of ways second segment can be placed is ZP. From third to the last, which is X set, how many different ways you can add? You can add, it is basically the same way. It is basically the way, same way you have added the second one, you have to add third, fourth, fifth, sixth, X, the same way you have to arrange. So, they all, each third segment can be placed again by ZP way, fourth segment can be placed in Z multiplied P ways and so on. Okay. So, total number of ways then. So, the total number of ways the polymer segments of the I plus first chain can be placed will be given by the multiplication of this all these segments, first segment n 0 plus x I, second segment Z P what I just missed here is that when you have a one second sample can be placed any of this Z coordination number, but the third one is, for the third one is already blocked, one of the Z is blocked. So, from third to last will be Z minus 1, because 1 is already blocked, one of the neighbors is already blocked. Okay. So, if I place third here, I can place third here, I can place here, I can place here, I can place here, one of these already blocked, I cannot place here. Okay. So, it has to be Z minus 1, fourth one again Z minus 1. Okay. So, that is you have to remember. So, z minus 1 p. Okay. So, now so this is for the first segment, this is for the second segment, and this is for the third to the last segment. Okay. Now, what I will do, I will quickly go through the mathematical part, which not plus, this minus, sorry. Now, z, because z is quite high. So, I can again z, I can put z equals to z minus 1. So, I can make z minus 1, z minus x minus 2. So, that is x minus 1 and p x minus 1, and we know p is n 0 minus x I by n 0, that is x minus 1. So, I can rearrange it x I, bring that here x and z minus 1 n 0 x minus 1. So, this gives the number of possible ways this I plus first chain can be introduced in the lattice. Okay. When the lattice is already has I number of polymer chains present. Okay. So, for simplicity, what will be the ith chains, number of ways the ith chain can be placed, n 0 x I would be I plus 1 is I. So, I would be I minus 1. Okay. So, this is the number of ways this ith chain, ith polymer chain can be placed in the 3D lattice. So, now if you want to calculate the number of ways all these chain can be placed, we have to multiply by the possibilities of each individual chain. So, the number of ways, total number of ways the polymers can be placed in the 3D lattice will be given by W1, W2, W3, Wi, Wn2. Okay, now, one thing you must have noticed that what we have considering here, that when you finding the probability P, we are just taking that the chance or the probability of one cell being vacant is the number of vacant cell divided by the total number of cells. Okay. Now, polymer chains in actual sense is this all segments are attached. For a single polymer chain, the all segments are attached. So, in true sense, the chances of finding a vacant set nearby a polymer chain would be lower than from a distance from a chain. Okay. What I am trying to explain, that the chances of finding one vacant cell near the polymer segments or near a polymer chain would be lower than if you go little distance from a polymer chain, because the segments are attached. But we are not considering that, we are considering that whatever polymer segments are already present, they are distributed randomly. Okay. So, that is the assumption we are making, and we are telling that is mean field approximation, where we are considering that all the segments which are already present in the 3D lattice are distributed randomly. They are not joined, they are distributed randomly. Okay. So, we can found the number of distinguishable ways all the N2 number of polymer molecules can be placed, be WP would be, because each again like the ideal solution, the arrangements between a single polymer chain are identical. So, you have to divide by N2 factorial by the total number of arrangements. These are the total number of distinguishable arrangements. Now, I am not going in details about the steps for these mathematical steps. You can get or you can refer any of the standard textbooks. You will find out the different steps in between. I am going directly to the final expression of this number of ways this total number of N2 chains can be placed in this 3 lattice, which is number of distinguishable ways you can place the N2 number of molecules in this state, it given by the expression we just mentioned here. Now, we just drop the steps and write the final step. So, this is the number way these all the polymers can be placed. Now, once we had placed all the polymer molecules, now we can place the solvent molecules in the vacant cells. Now, how many different ways the solvent molecules can be placed in the vacant cells? All the solvent molecules are identical. So, there is only one way you can place all the solvent molecules. If you change the places between the solvent molecules themselves, there is no it does not give any indistinguishable arrangement. So, there is only one way you can place the solvent molecules. So, the total number of ways you can place both the polymers and the solvent molecules and complete or fill the 3 lattice will be given by this multiplied by 1, which will be this. Okay. So, W, which is the total number of ways the total entire 3D lattice containing N1 solvent molecules and N2 polymer molecules can be filled is by this way. So, what will be the entropy for this combinatorial entropy for this mixture would be K ln W P ISM by K ln W P would be given by minus 81 ln Okay, so, this is what we get. Now, what would be the, this is the Sm is the combinatorial entropy for the mixture of N1 solvent molecules and N2 polymer molecules. Now, what will be the S or combinatorial entropy for the solvent? Again, the number of ways you can arrange different solvent molecules is 1. So, it will be KLN 1, again 0, number of different ways you can arrange the solvent molecules, but unlike the ideal solution case, S2 is not equals to 0 here, because the polymer amorphous polymer chain has different conformations, and so you can actually arrange the polymer chain in different ways, okay, not only one way like small molecules. So, S2, which is the combinatorial entropy for the polymer molecule, is 1, is not equals to 0, it has significant value. So, what I will go, I will continue, I just take this, do one more step, mathematical step for simplification. Smk is minus N1 these are simple mathematical step, I am not explaining, which you can do yourself, and so for pure polymer into N1 is 0 and pure solvent into 0. So, S2 for the pure polymer we can get from this expression just by putting N1 is 0, which should be N2 x minus 1 ln z minus 1 E plus ln x. So, delta Sm, which is mixture minus S1 minus S2, would be given by minus K, this is the term, same term, so would be given by K ln N1 N1 plus x N2. Okay, let us do it in the next page. Now, N1 by N1 plus x N2, we can write this as phi 1 is a volume fraction. Okay. This is the total number of segment, N1 is total number of molecules, and we knew that the volume or size of a segment is same as the size of a solvent molecule. So, this would be the mole volume fraction of the solvent, and this would be volume fraction of the polymer. So, we can write this N1 plus N1 then phi 1 plus N2 then phi 2, or you can get N1 So, after all this exercise, we got this entropy of mixing for the polymers in a solution is given by this expression, and this is expression is same as the ideal solution of small molecules, because in case of ideal solution we knew that phi I is for an ideal solution of small molecules, phi I was equals to the mole fraction, volume fraction was equals to mole fraction. So, you can replace by the mole fraction this number, it gives the same number. So, what this expression we can just what we will do, we will just come back in the next lecture, and now by we understood that by Florey-Huggins approach we can find out the entropy of mixing for a polymer and a solvent. So, we need to find out the delta H mixing or enthalpy of mixing for the polymer and solvent, so that we can get the free energy of mixing for the polymer solvent mixture. So, in next lecture we will first get the enthalpy of mixing and then proceed from there to get the total Gibbs free energy of mixing for a polymer and solvent system.